In this video, we want to take a look at the mathematical description of the one-dimensional position function. Now, this really is pretty straightforward, and so I want to spend a little time just to be clear on notation as we go forward to distinguish position functions from specific positions, etc. So, as we described qualitatively, the position is a vector function of time. We represented it by the r vector, looks like that. And in fact, we'll look at one of our examples where we had, say, this is the plus x-axis, and we had a car that was moving and, say, accelerating then in the x direction. And we sort of looked at a tabular form that at time 0 it was at 0, 1 it was at 2, this is in centimeters, and 2 this is 8, then 3 it was at a position 18. And if this is a continuous function, so I write that r as a function of time, this vector has a magnitude that's equal to 2 times the time squared, and that's in centimeters, and it has a direction in the positive x direction. This function now provides the not only the positions identified in this table, but the position vector for all time. Now, if we're working in one dimension, we'd like to use a notation that is much simpler. Since it only ever exists on the x-axis, I can rewrite this function to say, well, it's the x location of this particle at any given time is simply 2 times t squared. And this 2 times t squared is in centimeters. And this now gives me the x-coordinate of the position of the object at every time. And this is a lot more convenient than to write this vector notation everywhere. And so this is what we like to do in one dimension. I'm emphasizing this because this looks a whole lot like a scalar. And it's not. It's just a shorthand for the vector represented by the yellow vector function here. It's telling you the location at some given point in time, which would be the tip of a vector from the origin to that location. And so we certainly want to use this notation. It's a lot simpler, a lot easier as long as we're working in one dimension. But just never forget that it still represents this vector at t is equal to 1, then, of course, as we see, then I plug this in here. This is 2 centimeters. But that represents this vector that starts from the origin and points to x is equal to 2 centimeters. It has a magnitude of 2 centimeters and a direction in the positive x direction. Okay, so let's just look at another simple example. In this case, I'm going to have a person on a cliff throw up a ball. It goes up some distance and then falls back down. Okay, so there's this ball, it goes up and falls down. So let's establish a coordinate system. We'll put our 0 of our coordinate system at the place where the ball launches. We'll have positive x going up. And I'm just going to tell you that the x-coordinate at any later point in time is given by 15t minus 10t squared. And this is a position, and it is in meters. And so this is the one-dimensional function that tells me the position x at any point in time. And so, for example, x at 1 is equal to 5 meters. If I put in 1 here for t, I get 15 minus 10, and say x is 2. That gives me, that's 30 minus 40 is negative 10 meters. And so again, these represent vectors. And so, for example, at, let's say, at t is equal to 1, the object was here. And so this represents the vector that has a magnitude of 5 meters, that points in the positive x direction. And now at t is equal to 2 seconds, the object is located, say, here. So this is t is equal to 2. So this, x is equal to 2, represents this vector that starts at the origin and points to the position x is equal to negative 10. I can represent that by a vector whose magnitude is 10 meters pointing in the negative x direction. So you see how this works is that as long as we're in one dimension, there are only 2 possible directions for our vector. It can either be pointing in the positive x direction or in the negative x direction. And so we can represent that vector in the shorthand by these numbers, say 5 meters or negative 10 meters. And this is sort of a vector shorthand where the magnitude is this number, either 5 meters or 10 meters is the magnitude of the vector. And then the sign gives us the direction. The positive sign tells us that it's a vector pointing in the positive x direction, and the negative sign tells us that it's a vector pointing in the negative x direction. And so, even though it looks like scalars, these functions are still vectors where the sign of the number gives us what direction, either the positive or negative axis, that the vector is pointing. Okay, so one more thing I'll point out just from a notation point of view is that a lot of times we're going to be looking for specific points in the trajectory or specific points in the position function. And so this now is the position function. It's the position function for all time. But let's say I was really interested in these 2 points in time. I can say, well, there's some initial time, which is equal to 1 second, and some final time, which is equal to 2 seconds. And in that case, I want to know what the position vector was at those times. And so I might call the initial position x sub I, which is equal to the position function evaluated at t sub I, which in this case was equal to 5 meters, which represents a vector of magnitude 5 meters pointing in the positive x-axis. So I might also be interested in what I call the final position, which is equal to the position function evaluated at the final time, which in this case at 2 seconds was equal to negative 10 meters, which is again a vector as we described before. And so because of this, I might be interested then in delta t, which is the time difference between these 2 specific points in time. That's t sub f minus the final time minus the initial time, which is equal to 1 second. I could also be interested in delta x, which is equal to the final position minus the initial position. This is the displacement, again, which in this case is equal to negative 15 meters. So this is now the displacement as we described before. This is a shorthand for a vector. It's a magnitude of 15 meters. It points in the negative x direction, but we calculate it just with our scalar arithmetic because we are only in one dimension, where the sign takes care of the direction of the vector for us. And so one of the key things I want to point out here is this distinction between x, which is the vector function of time, t, which is an independent variable, it can be any time, as well as when we decide we want to choose two specific points in time, t sub I, t sub f, which gives us two specific positions in time, x sub I and x sub f. We can calculate the time difference, we can calculate the displacement, and all of those come from specific choices about these two specific points in time and how that is distinct, and how we get there from our position function and how to distinguish it from our position function of time.